Um, Thank you very much, Amarnath. It's a true honor to be here with you, discuss our research on friction-based force limit connections. Overall, our research group focuses on contributing to the improvement of resilience and safety of our built environment and educating the future structural engineers, mainly working on experimental, computational, design, and hybrid manufacturing research methods. And today I want to focus on the left-hand side, the experimental work we've been doing. And my goal is to share findings from friction-relating experimental research at material, component, and system level that we have been working on since 2011. More specifically, the goal is to share aspects of the benefits of using friction-based connections in structural systems, share the challenges observed through experimental tests, and also talk about how we can address these challenges also through additional experimental research. I have to acknowledge a lot of people here. I was grateful to be one of the students early on in 2011 on a big project under the supervision of Richard Schoss at Lehigh University, on a project led by Robert Flashman, and then obviously my students at UCSD, and especially Kai-Sin Chen, who is doing all the hard work in the lab, that some of it I will show you today. And also the NCRI team in Taiwan, along with Professor Chu, Chao, and Wang, where we did a shake table test in Tainan. I won't talk about design at the system level. However, we have a project funded by NIST through the Disaster Resilience Research Grant Program on the resilience-based design of buildings with accelerated post-earthquake functional recovery that take advantage of the utilization of friction-based connections efficiently placed in the seismic load path. Now, friction is not new for sure, and ICANN is listed here. To my knowledge, Clark was the first one to introduce the notion of friction to limit forces in foundation settlements. And then I list only 20 years worth of research, mainly on bimetallic friction interfaces for structural engineering applications. A lot of work obviously was done here at UC Berkeley, so it's a true honor to be here. An example application span from bridges to all kinds of building structural systems. And it's a simple notion of having steel components bolted together and allow these plates to slide relative to each other. That's it. But today I want to discuss how we get from this type of behaviors that are far away from the friction Coulomb type of behavior to something that it's more desirable and stable with respect to long-term and short-term performance. And also, our goal essentially is to enable structural engineers to design their own version of friction components, because it's not complex at the end of the day if you know what to look for. All right. So in our case, in our research, we use these friction-based connections, and we call them force-limit connections for a reason. They're not fuses or dampers, to transfer seismic-induced inertia forces from the floor diaphragms into the vertical elements of the seismic force-resisting systems. These may be rocking braced frames or rocking walls. So we use these connections distributed over the height to control the higher mode responses, and the force-limited connections, the friction-based force-limited connections at the base rocking mechanisms control the first mode response. So you have a very clean seismic load path with controlled forces, and that reduces the uncertainty in our ability to design these systems. Again, I'm not going into this topic, but it's something that I have deep interest. For this structural system, I saw here half-scale 4-story precast rocking shear wall structure that was tested at UCSD, and I was a student involved on the designing these connections. And on the left, you can see the fourth floor friction device transferring the load from the floor into the precast rocking wall. And this is one of the tests. So the specimen was subject to MCE level ground motion recorded here at Berkeley. So you see the 4-story friction device and its kinematics, so the connection between the floor into the precast rocking wall, and the force displacement behavior. So this is nice, relatively nice, I guess, stable frictional behavior. It's not that easy to get there, especially at this low force level, around 20 kips, and I want to go you through this journey on how we got there. Now, you will wonder, why should I bother using friction? Because metal plasticity and yielding mechanisms are very, very well established. There are some benefits. I believe that there is freedom in detailing if you know what you are designing for, and there are many forms that you can accomplish the same thing efficiently. And if you know that, then you can have a very large span of force levels with minor adjustments. The principles remain the same, and we have tested from 1 kilonewton, like toy structures, to up to 1,000 kilonewtons. And we use exactly the same principle, but considering the things I will discuss with you today. And the nice thing is that you decouple the stiffness from the strength, essentially. You can have a very high stiffness that is not affected by the sliding force, which is one of the topics that you have to consider in yielding mechanics. Like the stiffness and the yielding force are coupled. Now, it is possible to have easy manufacturing and assembly for these components, and I put an asterisk next to manufacturing because it can be easy, it's not always easy. And here's an example of what can go wrong. So on the upper figure is the wrong, and the bottom is the right. On the right-hand side, you can see a force displacement behavior that's not actually friction Coulomb type because you get some strengthening, I guess, with respect to the displacement. So your force is basically coupled to the displacement. This is because on these components, we have no tolerancing for the machining of the parts consist this connection. So there was an imperfection for the parallelism of the slots. So you can imagine when the bolt slang was when the bolt was sliding in the slot, was coming and bearing against the slot, and there was an additional friction force that was secondary but significant for this force level. If you develop a full-scale device for thousands of kilonewtons, this secondary effect may become insignificant, but it's good to understand what happens. And one way to solve it is just to have tight tolerancing requirements, like 0.02 of an inch for flatness of plates and parallelism of slots, and you can get a nice result like the one we got on the SEC table. There is an alternative method that's much lower cost, which I will discuss later. Now, the increase of displacement capacity is not tied to any strain limit. You just increase the slot size, and that's it, which is very convenient. And some designs are low damage and have access for repairability, and an asterisk there because it's very related to the design, the detailing of this configuration. And some design are damage tolerant. And here I show basically one test that a fracture of the composite friction plate occurred, and then we kept testing, 10 tests later, similar frictional behavior. So this is damage tolerant, although we don't want it and we design against it, at least there is some safety there. Now there are some challenges. The grass is not green all the time, and if we understand those, I think we can do better. So there are challenges with respect to the dependency of the frictional behavior with respect to the sliding velocity, and that's not instantaneous in our case. It's the absolute maximum with respect to the wear mechanisms that develop in that friction interface. Is the dwell time. We know that galvanic corrosion may establish in bimetallic interfaces, so that's why we personally move away from that. But if you use composite materials, then you have creep effects. You have braking and cumulative sliding coming into play because they control the wear mechanism. And as we discussed, machining and geometric tolerances are important. And then this is, I guess, that has a duality. The effectively zero post-elastic stiffness can be good, can be bad. If you do capacity design, it's nice. If you don't do capacity design and you want stability at the system level, you may want some secondary post-elastic stiffness. And in order to address that, I will quickly say that we have developed a modified friction device that establishes predetermined discrete variable friction forces with the notion of performance-driven displacement ranges. So someone can say at this displacement range, which I expect dB level motion, I want that level of force. At MC level range of motion, I want higher force. And it's relatively practical, easy to do. And we have been working on this with Kaisin. So let me go back to these challenges and start explaining one to one and address them, how to solve them. The velocity dependence. So here I have plots that indicate the absolute friction force that we measured, so it's the force, total force in the component, the absolute displacement to get a sense of the magnitude of the displacement, the absolute velocity to see how much it varies with respect to the test, and the cumulative deformation. So the green arrows point to some of the tests that were quasi-static, very slow motion. So there is this trend where we converge to a steady-state friction force that is about 10% higher than the target friction force that I call Fs there. And then if you run dynamic tests, which are where the arrows are pointing, you see that we have convergence to 85% of that target friction force, and it's consistent. And these, I think, are interesting experimental results that require a little more attention. So if you dive deeper, and on the upper plot I show the velocity aspect, so it's a normalized velocity, and I want you to track the red dots, which are the overall maximum peak velocities in that test. And the yellow dots below are the average values of the friction coefficient. So as you see, as these red dots go up, the friction coefficient goes down, and they both converge and they remain stable. As the velocity, the blue market, goes down, there is no increase in the friction coefficient. So it's not instantaneous velocity dependence, right? It's a cumulative effect. So let's think what may happen there. So it's a hypothesis coming from tribological theories. Tabor and Bowden have done a lot of work. So let's think when we establish the friction interfaces, and let's take one asperity, we have a true contact area that has some frictional strength or shear strength. As we shear that interface, we increase that true contact area without generating a lot of degree. At least the generation of wear is slower than the evacuation capability of the interface for that wear. So we have a larger true contact area with the same frictional strength, and that means higher friction force in our eyes. And if you start sliding this interface faster, which is the last graph there, you start generating debris very fast, and you cannot evacuate it fast enough. So you created a thin film that not only has a smaller true contact area, but has also less shear resistance. That means you get that drop to 85% shear friction. Okay. So having that in mind, our goal is to find materials that we can establish friction interfaces with better long-term performance that are less sensitive to these properties. So what we've done to address the material aspect is done a thorough, if it moves forward, okay, too much. A systematic experimental study among 6 different composites, which are ferronic resin-based composites that are reinforced either with e-glass fibers or cotton fibers, and we use different friction modifiers. These are made by our colleagues, and we use them and assess basically the effect of constituents in the frictional behavior. But not only that, we did mechanical characterization. Obviously, we track the ball loss, which is very important in friction connections, and also the tribological aspects through friction tests. I want to focus on the ball relaxation tests, which are basically clamp plates, and we used all these 6 specimens, 2 ball load levels, about 1.5 KSI average normal stress in that interface for the high ball load, and 1/3 for the lower ball load. And then we tested 3 specimens per material. We had a baseline, which was just plain steel, and we waited till convergence of the ball load was established. These are the results, and in summary, you can see that the ball load for obviously the steel case, which was the baseline, was the lowest, which was expected. And then all the composites had between 5 to 15% ball load loss. And there was no clear correlation between the constituents of the materials and the ball load loss. However, there were these outliers again that create the interest. So you can see one example was the Gatke 112, which is a cotton fiber-based composite, that we want to understand why this outlier is there. So what Kaisin did is went in the lab and took pictures from a section of that plate that did not have issues with high ball load loss, and some sections that we had high ball load loss. And he saw that there is a low volumetric ratio of phenolic resin in these cases that we had high ball load loss. And that means that the process, the flash compression molding manufacturing process that we use, forces all the resin out of the edges, and you end up with a bunch of fiber without any resin. And that basically creates a situation where you have basically a more flexible region and appears everywhere. One example is if you take pressure films, you can see the high concentration of normal pressure in that region where we try to compress that particular part. So there is importance in the quality control of these elements if you actually want to use them in a friction-based component to ensure long-term performance in the ball load you expect. And with respect to the friction test, we did exactly the same thing. We came up with a setup that allows us to test different materials. We used all 6 different materials, 2 normal load levels, and we collected all our data. And moving fast forward, I guess I will focus on the velocity dependence. And we understood that materials that are phenolic resin based with e-glass fibers and graphite, Teflon, and molybdenum tile sulfide as the friction modifiers that control the wear mechanics result in the most stable frictional behavior with respect to velocity, braking effects, and all the things that we discussed earlier. So you see this basically line here is for that particular material that appears to be almost insensitive on the velocity dependence. And last thing I want to touch quickly is the machining and geometric tolerancing. We proposed one solution, do a good job in machining, controlling the tolerances. They will ask you to pay more, obviously. But we want to come up with a very low-cost solution that is insensitive to geometric tolerancing. So what we did, and that's the project with Enkri in Taiwan, we had to connect a sliding floor slab to a steel moment frame that had to remain elastic. So we designed, in 2.5 weeks, that's the cycle that I'm showing here, we designed a component that is able to do that. We did some finite element analysis to capture the strain distribution around the components that we want to remain elastic to ensure that the design meets our requirements. And then we developed the numerical code required to machine the parts in order to justify that we understand what it takes to make them, and we can claim that they are easy to make and low cost. And then we went to our lab that we have all kinds of manufacturing equipment to evaluate how easy it is. And if we can make it, then people that do this for a living obviously can do it. So we demonstrated this, and then we went in our lab to capture the force displacement behavior. So here you can see that the force level is relatively low, and this is where you expect all these geometric tolerancing effects to control. But the loop looks like a friction Coulomb behavior. And that cost 1/10 of the cost of the next device that we tested at the shake table, which should come up now. Yeah. In Tainan. So this is a friction device connecting the floor diaphragm with a steel moment frame, and you may see some sliding up on the top floor there. So that cost around $400, I guess, to make. And the last piece is repairability, I guess. I put an asterisk next to it because there are some designs that are easily repairable, some other not, if it comes up. It's
stuck?
Yeah.
Okay. Experimental session, so things do go wrong occasionally.
Yeah.
Okay. Okay.
Yeah. So here is the visual demonstration of repairability. Just because of the design, which is the concept of putting loose plates to establish the friction interface, allows us after 10 earthquakes or even MCE ground motion to go on the table, on the specimen, and in 3 minutes basically open up the friction interface, inspect it, and that's more of a demonstration. Make sure that the wear is as expected and put it back together and continue. And with that, I would like to really thank you. It's an honor to be here. And these are some of the references from the work we've been doing.